To recap, in the last talk, we basically said we needed this, right, for design drivers. So we're going to focus now on technologies in this 10 millieV to 10 GeV range. And we said there was a few things. So we needed sensitivity to tiny excitations or some kind of tiny energy. We needed very small dark count rate. And we needed that dark count rate to be Poissonian and not non-Poissonian. And exposure wasn't a big deal. You could do a kilogram year and you're fine. And radioactivity also is not a huge deal. You can do 1 kilogram per day per keV if that's your background, Compton background, and you're good to go. So it really comes down to how do you get those two. And I'm going to talk about how you get those two in calorimeters and what were some of the mistakes that people have made with calorimeters over the past 30 years. And also just explain how calorimeters work. So what is a calorimeter? So if I put a little bit of energy into a heat capacity, the temperature goes up. So the change in temperature is just delta E divided by C, the heat capacity. And I can actually say if I make a sensor out of a heat capacity and I toss a thermometer on the side, how sensitive could that be in the ultimate limit? And there actually is a nice StatMech version to actually figure out what this is. And it's just to say if I have a heat capacity connected via a thermal link in which energy is flowing back and forth between the bath, what is the fluctuation in energy of this heat capacity? And this is literally just a StatMech problem, right? So you can calculate it through, and you find that the variance in average energy of this heat capacity scales as C kVt squared. So this says that if we want to do this and we want to make a calorimeter sensor, what do we want to do? Well, we want to minimize T. So this is why we're not going to make a calorimeter out of a room temperature, bottle of water. It's because the T is too high. And so we're going to want to go to basically absolute zero, or as close as we can get to it. And really, there's a place where we can get to, which is 5 milliK. And that sets the threshold of how far we can get before things get really difficult. So you can get to microkelvin, you can get to nanokelvin, but that's a big challenge. Dilution refrigerators just automatically get you to something like 5 or 10 milliK with only an obscene amount of work, not crazy obscene amount of work. So we're going to basically try to set right there. And then now what about the heat capacity? So previously we were talking about, on the previous slide, we need kilogram year exposures. With the first prototype things, we need gram days. That's still a gram, right? And on the scale of LZ, that is 6 orders smaller, so it's trivial. On the scale of a single pixel of sensei, that's enormous, right? A single pixel of sensei is like 25 microns across, let's say. And so those are microgram and nanogram per pixel. So this is actually it's depending on what side you're coming from. 1 gram day is actually a huge exposure or a very tiny exposure. So for us, if we want 1 kilogram year or 1 gram day, we're definitely going to want to keep the volume of this C small because C scales with V. And we can't make it too small because, again, we need that 1 gram day. So our next trick is to use a low T insulator. And so electrons, so metal systems, they have a heat capacity that goes as T. So your metal heat capacity goes as T. Your insulating heat capacity goes as T cubed. Those are both easy to see. So let's say to just calculate in your head why the heat capacity for an insulator goes as T cubed. You can just say that the phonons, omega K relation, so for that acoustic branch of phonons that we talked about, omega, so the energy is equal to the momentum times the speed of sound. So E equals PV. And now you say in a certain volume of energy, how many phonon modes you have. And that's just a sphere, right? So basically, the number of modes, of vibrational modes you have, scales as 4/3 pi times times E cubed. And then you have how many, and then each mode has on average E amounts of energy. So that's 4/3 pi E cubed times by E, or it's E to the 4th. So the total average energy in the phonon system goes as E to the 4, or the heat capacity goes as E cubed, or E. And there we are. Awesome. Okay. So this thing goes as E cubed. So that means as we go to very low temperatures, the heat capacity of this absorber goes to 0, and it doesn't affect us. So for the last, let's say, 30 years, we've been saying, let's take a thermometer, which is an electronic system, and let's couple it to an absorber, which is an insulator. And therefore, we get the gram of material we need, the 100 grams of material we need, but we don't pay any energy resolution penalty for it. So this has been the idea for 20 years. And here are the plots of, this is basically the energy resolution that we would expect. This is C kBT squared. So here is the temperature of the sensor. And here is the baseline resolution measured. And these are those curves that we would expect. These things are scaling as C kBT squared. And here are the actual experimental measurements. So this is what it should have been, and it was up here. This is what it should have been, and it was up there. So we have this 2 orders of magnitude difference between what was expected and what people achieved in these sensors. And the question is why? Why, for the last 20 years, have people not achieved the resolutions that they expected with this kind of system of an insulator coupled to a TS? And I would say the majority of the groups failed in this manner. And so I have this sensor, and the sensors we all use are electronic systems in some way, shape, or form. So I need to get the phone. So I have energy come in, hits the absorber, it bounces around, it thermalizes, and I have to get it into the electronic system. So here, that energy is in the vibrational system of the absorber, and I have to somehow get it into here and read it out here. And the problem is I have to go, therefore, I have to have a coupling from the vibrational system in the absorber to the electronic system in the sensor. In my case, it's a TS, but it could be an NTD. It could be any kind of system that I'm trying to get the energy into, but I'm always trying to get into the electron system of something. And this coupling here is going to be the electron-phonon coupling in the material. And it turns out that coupling scales as T to the 5. So the lower in temperature I go, the worse these two systems are coupled to each other. So if I want to go to super low temperatures to have really excellent sensitivity in my thermometer, the penalty is I decouple my thermometer from my absorber. And so this is a bummer. This is what people have been doing for the last 20 years, and they ask themselves, why don't I have good energy resolution? And now it's sort of obvious. I put energy in here, it bounces around, it goes out through the clamps of the housing, and then you lose it. Or a little bit of it comes here, but then they've coupled this electronic system directly to the bath through some kind of gold wire bond. And again, then I have noise here bouncing back and forth that totally dominates my signal. And this is the core. This is, I would say, the vast majority of groups that have tried to do this have made that blunder. That it seems like such a great idea to use this coupling because everything works out, right? Intrinsically, this gets more sensitive as T goes down. Intrinsically, you lose heat capacity here. And it just comes out that you can't couple the two together. And this is pretty much, we believe, the failure of why every group hasn't achieved the resolutions they hoped. So what is our solution to this problem? And I'm going to actually go to a different device completely. All detectors at some levels are exactly the same. Like if you saw the LZ TPC, in many ways that looked very similar to the Sensei CCD, right? In both cases, you had a large E field. Something came in, produced an electron hole pair, which drifted across. Like if you didn't know the scale of one was a meter and the scale of the other was a micron, you wouldn't tell the difference between the two. Here, this is true in so many of our detector technologies. So here we're going to switch over to a PMT and a scintillator. And let's think about what's happening here. The question I want to ask you guys is, which I give you the answer, which is I guess a little bit shady, is will these two systems, one has a giant crystal connected to a PMT and one has a very tiny crystal connected to a PMT, will those have the same energy resolution? And if they do, then that's awesome for us, right? Because that means that we can scale the exposure up without increasing the noise. And I think that the two things that one needs to have to scale up is one must have that. So here, an event comes in, makes a photon. To have this PMT only cover 1% of the surface area, what I need is I need that photon to bounce around on average 100 times before he's collected. So if, let's say, this surface is not reflective and it can absorb that photon, then these two will have vastly different sensitivities, right? So what do people do? As we just talked about, they wrap crystals in Teflon because Teflon is 99.9% reflective, right? So that makes these two, it makes that photon bounce, and then I can match the two. So what else do I need? I need the lifetime of that athermal excitation to be long. So again, if that photon can only travel, I don't know, 20 microns before he's absorbed, and this is 20 microns, and this is, I don't know, a meter, then I'll never get any of these photons out to the PMT. So these are the two things I need to make an excitation detector. The same philosophy works with LZ and TPCs, right? Like if LZ has a xenon TPC and it's a meter long, and the length of travel that electron makes before it's absorbed is only 2 centimeters, I won't see any of those electrons. So I need these path lengths to be the same size as the crystal. But if I have them, then my detector becomes insensitive. The energy resolution of my detector becomes insensitive to the size of the system. And that's what we want to do. We want to have that kind of system. And here is the basic idea that we're going to follow. So I have a dark matter particle come in. It hits my germanium or my crystal. It produces a bunch of athermal phonons and athermal vibrations. Now those vibrations start to thermalize, and they start to downconvert, and they start to go to lower and lower energy. But that process goes as T to the 5th. So once those athermal phonon vibrations get to an energy scale of something around 10 Kelvin, then they start to free stream. And this system looks identical to the system that we saw previously, which was a PMT wrapped with Teflon. So now these photons just start to bounce around like this. And they're bouncing. And then we cover a certain fraction of the surface with an athermal phonon sensor. And it is basically a phonon comes in, it interacts with an aluminum superconducting film. That aluminum superconducting film, this athermal phonon will break the Cooper pairs in this film into 2 quasiparticles, turning the phonon's energy into this gap energy plus kinetic energy of the quasiparticles. Those quasiparticles will then bounce around, and eventually they will get pulled into a little tungsten TS, which is just an electron film, which is a glorified thermometer. We could use anything to measure out the temperature, but we're going to use a transition sensor in our group. So what happened here? Notice that the coupling of this athermal phonons, it occurred at 10 Kelvin, not at 10 milliK. So the coupling was enormous, that electron-phonon coupling. We bypassed that problem that we had earlier in this slide. In this slide, the problem was the electron-phonon coupling was horrid at 10 millik because its scale is t to the 5. Here, now we have, in this system, our energy scale of all of our phonons when we're coupling is at 10 Kelvin. So now we can couple them in incredibly easily. And every phonon that gets into the aluminum, 1-to-1 interacts with an electron and gives us quasiparticles. So the final thing we needed to make this bouncing is we needed to make sure that these things have very long lifetimes. And below 10 Kelvin they do in terms of the bulk anharmonic decay. But the question is what about the surfaces? And this is a fundamental question, which is very important. It turns out that the probability of thermalizing an athermal phonon on the surface, it scales with the roughness of the surface, and it scales with how clean the surface is. So if your surfaces are very clean, we've shown a limit on the number of bounces of something like 1 in 200 is the thermalization probability of an athermal phonon on the surface of our crystals in germanium and silicon. But it could be even higher. It could be thousands. And that is something that is a current level of research is what is, at a super clean surface, what is that thermalization probability? So can we get to Teflon, where Teflon is 99.9% reflective? Can we do that with a crystal surface? And if we can, then we have that ideal system. So let's look at some signals here. So here is the phonon signal in a giant super CDMS prototype detector. So think 100 millimeters big, 1 inch thick, 25 millimeters thick. And the signal here has a fall time. And its fall time is 210 hertz, or 750 microseconds. And I'm giving these numbers just because they are going to be important in a second. And what we find is that as we change the amount of aluminum on the surface, we change this signal. We change this fall time. So if we double the surface area, the amount of aluminum on the surface, we double the bandwidth of the sensor, or the fall time becomes a factor of 2 faster. The fall time is a factor of 2 faster. Tau is a factor of 2 slower. So what we're saying is this fall time here, this is literally the athermal phonon collection time that you're measuring directly. Okay? And this is one of those things when you have an experiment and you have a fall time in your system, you never know what it is, right? Is it because of your electronics? You put an extra filter in your electronics. There's all sorts of ways that one could get a fall time in your signal. But here we've matched it to the aluminum coverage, and we see the intrinsic fall time. The fall time we're measuring of our pulses is intrinsically limited. It's the amount of time it takes the phonons to be collected.
So, good question.
Yeah.
Does it depend on how you support your?
No, actually, let's think about that. No, that's a great question. The question was, does this fall time depend on how we support the crystal? So let's think about that. We are going to hold our crystal with some clamps. And the clamps have something like an area of the surface interface is something like it's less than 0.1%. Or I'm sure it's actually, I must say I've never even calculated it. It is less than probably 0.01%. So it's less than 1 to the minus 4 of the surface coverage is actually the clamps themselves. So when you think about that, what are the odds that that athermal phonon will actually go into a clamp before it gets absorbed on the surface? The surface is 6%, or here it's 6% aluminum phonon sensors. The clamps are 1 e to the minus 4. So the clamps just don't matter. That phonon will always be absorbed by the sensor. As you go to smaller and smaller devices, that becomes more and more important because you can only make the clamps a certain size before it gets physically problematic. No, so this is actually historical. We prefer big things because we were competing against LZ and we wanted to do high mass WIMPs and high mass exposure. Once we couldn't do high mass WIMPs anymore, we were somewhat stuck with this form factor of 1.5 kilograms. And luckily, we can live with it. But in some sense, we would ideally, if we were redesigning from scratch, we would want to shrink it down a little bit because we don't have the exposure problems that we have per the talk previously. Okay, so now we know this fall time, and this is literally, the fall time of this is the collection time for those phonons. So let's talk about something else. Now let's talk about this transition head sensor, this thermometer. So it has a fall time too. Its fall time and its bandwidth is just related to the C over G of the system. So if I put energy in here, what is the time it takes for that energy to get into the bath? There's a characteristic time constant, which is C over G. Or the bandwidth, 1 over tau, is 4 kilohertz. So notice right now that V signal is much, much less than V sensor. This is a key thing you need to understand. So what about noise? So there's 2 different types of noise that are fundamental to our devices and to pretty much every device. One is Johnson noise, and we're using a change in resistance. We're reading out a change in resistance that change with temperature. So we have Johnson noise associated with that device. We also have the equivalent of Johnson noise, which is thermal fluctuation noise, on a thermal conductance, which is just the StatMech idea that phonons flow from the bath up to the heat capacity and back and forth randomly. And this noise scales as 4 kBt squared G. This noise scales as 4 kBt over R in terms of current. And what we see is actually at low frequencies, you're dominated by this noise if you design the system correctly. And at high frequencies, above the sensor bandwidth, you're dominated by the Johnson noise. So I told you previously that for all athermal phonon systems that we design, your sensor bandwidth is, and I messed that up. Your sensor bandwidth is greater, sorry, cover this up, guys. So here is all the systems. I told you the V sensor, the sensor frequency was greater than the signal frequency. And I've also told you that the sensor frequency scales with G. So I can choose to have 2 different systems. I can choose to have a high G system, which is here in red, which has high sensor bandwidth, but also high DC noise. Or I can choose to have a low G system, which has low sensor bandwidth, and, but has very low noise. And if my signal is all very low frequency, then I want a bandwidth match. I want to say, oh, let's drop my sensor bandwidth to my signal bandwidth. I want to make these things go together. And I want to design a system that is down here. So you just go through the math. Your G goes as T to the 4. Your noise, the thermal conductance. Your G is your thermal conductance, goes as T to the 4. Your noise goes as T squared G, so it goes as T to the 6. And that means that your energy resolution in this limit, where your sensor bandwidth is bigger than your signal bandwidth, scales as T cubed. So as I drop this down, as I drop G, as I drop TC, my V sensor goes this way and goes down. And the change here in a given bandwidth scales as T cubed. So it's an enormous improvement in energy resolution. You know, this says if I have my device at 100 millik and 10 millik, my 10 millik device should be 1,000 times more sensitive. And so this is this rule for athermal phonon devices that they scale as T cubed in this limit. And so basically the moral is you always want to match your sensor and signal bandwidth. Okay? So now finally we talked about optical phonon devices in the previous talk. So an optical phonon device is literally just basically the super CDMS device, just shrunk to a gram in size, right? So we shrink to a gram because we have this probability to thermalize on the crystal surface. And so we want to make our devices super sensitive. So we want to take the TS, and we don't want to put 100 TSs down. We want to put only 10 TSs that are very small in volume, because we want to make that C as small as we can. And so we're going to take a 5 millimeter by 5 millimeter by 5 millimeter polar crystal, put just a few sensors on the surface, and it becomes just like a super CDMS device, but just super tiny. So hopefully it'll have a much better energy resolution. And notice here that at some point, you can't play this trick forever, because as you said, you have to somehow clamp it, and then somehow those clamps are going to be phonon sinks. So you can only play this trick until you get to a level of the mechanical holdings of your system. But we think that actually a gram scale, centimeter cubes, are basically the scale that set that minimum scale for maximum energy resolution that one would like. OK, so that was just an aside for that. So now we have all of these pieces that we have. We have athermal phonon bouncing. And on the surface, we have these very sensitive calorimeters, very sensitive like thermometers. So let's just see how sensitive we can make these thermometers. And here, we've done this in my lab up at Berkeley. We took a bunch of little thermometers, and we just scaled the area by a factor of 4 every time. So we have here, 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 here. And in theory, the area scales as 4, the volume scales as 4. And we know that that very first slide I gave you was the resolution was CKBT squared. So every device should, in theory, have a factor of 2 better energy resolution than the one below it. And let's just see if we actually follow this rule. Here are actually just some statistics which show like how fast this device is behaving. Actually here, this is very important. This is that sensor bandwidth we talked about earlier, that C over G. Here we measure it directly by putting a jitter down the bias line. So we put a voltage jitter down the TS. And we can actually see what is the fall time. We just measure it directly. And we get 8 kilohertz. So these devices that I'm showing have a fall time of 8 kilohertz, have a fall time of 20 microseconds. They have a sensor bandwidth of 8 kilohertz. So they're still really fast. And if my signal is 200 hertz, they're still out of match. I'm still really showing you a blue device, and I want a red device, and I want a blue device. But at least we can start to see, if I bandwidth matched, what my performance would be. So here is the actual noise that we actually measure. And we're doing pretty good. So that basic intrinsic theory we talked about earlier, which was Johnson noise plus TFN noise, plus thermal fluctuation noise on the thermal conductance, that is basically these terms here. And I'm showing you in watts per root hertz. So it's a slightly different basis. But those two terms are the green, and the Johnson noise is the red. And here is the actual noise we measure. So there's something like a factor of 1.4 off from the theoretical. And the noise here is 2 to the minus 18 watts per root hertz. So if you plug and chug at 8 kilohertz, you find that this device has 55 millieV resolution. So we're starting to get into this range that we wanted, right? So like EV scale was the important scale we were seeing for lots of those devices. So for electron recoil dark matter, what was the important number? It was 1 EV. That was a semiconductor scale. So we're starting to get below that. Now this is without collection losses. So I want to warn you that in this process here, where the phonon comes in, interacts with the Cooper pair, creates 2 quasiparticles, that is something like 50% efficient. So on average, 50% of the energy goes into the Cooper pair system. 50% is radiated away into low frequency phonons. This process here of those quasiparticles diffusing, that's again something like 60% efficient. So you put all those together, and we get something like 20% efficiency throughout that entire process. So we think this number of 55 millieV is something like, right now, something like 200 millieV. So this device, which is really, really big, it was a 200 micron by 50 micron TS, is giving us 55 millieV energy resolution. And we could hopefully drop that down from a TC of 70 millik down to something like, 40 millik. And we could improve further by that T cube scaling that we just talked about. So this is optimistic, and it says that we should start to gain potential, start to gain energy resolution, and we should be able to potentially make all those devices we talked about earlier, that optical phonon detector, a detector that just has 1 eV sensitivity and can directly sense a single electron hole pair. The hope would be we could do that. So now I'm going to swap over to, oh, yes?
Which mass interval you are pointing to for this detector? How big?
Well, so I mean, right now our standard detector size. Oh, yes, sure. So the question is how much total mass one would want. And of course, a total mass is the number of pixels you can handle times by the mass of each pixel. So currently, super CDMS is basically a kilogram per pixel. And we're running right now, we have 6 times 4, so we have 24 pixels. So we have something like 24 kilograms, let's say, on that size. In the future, these ultra-sensitive devices will be gram scale pixels. And we'd probably like to put 1,000 in parallel. So maybe a kilogram, maybe 100 gram. That's circa that level you would need. But anyway, yeah, so that's the scale. So now let's talk. So far, that was this idea of just going in brute force, right? Saying, I want to make a device that is super sensitive. How can I do it? And the answer was, use these tricks of going to ultra low temperatures, use these tricks of athermal phonon excitation, and you could do it. Of course, we could also do it through amplification. And we could amplify that original signal. And let's see how we could do that. So there's this idea of loop-Negaunov charge amplification. And I think it's something that we use, but it's very similar to what we do in LZ. So it's sort of interesting. So let's talk about this, again, this idea of interaction products in a semiconductor, also in a noble gas. A dark matter or a photon comes in, interacts, it produces a bunch of vibrations, and it produces a bunch of electron hole pairs. The ratio of electron hole pairs for electron recoils and nuclear recoils is different. It's something like 1/4 of the potential of the total energy is put in potential energy of the electron recoils, where only something like 8% is put into the potential energy, into electron hole potential energy in a nuclear recoil. And therefore, you can ratio things. And you can ratio the amount of ionization you produce divided by the amount of phonon energy you produce to separate nuclear recoils and electron recoils. This is exactly similar to what LZ does, except they use scintillation and ionization. But the concept is largely the same. So the idea of loop-Negaunov phonon production is I take a photon comes in, it makes these electron hole pairs. I'm now going to drift these electron hole pairs across my crystal. And when I drift them, it's sort of like a parachuter parachutes to the Earth, right? When a parachute parachutes to the Earth, he hits a terminal velocity, and all of his gravitational potential energy is converted, not into kinetic energy, but it's converted into heat, right? Basically, he heats up the air. And this is exactly what happens here. So these electrons, they reach terminal velocity, and they are constantly giving off phonon vibrations. And those phonon vibrations we produce, we know exactly how many we produce. If an electron travels from here to here, he produces 100 eV of phonon energy. So we're converting that electrostatic potential energy into phonons. So the total phonon energy we measure is the initial recoil energy plus the number of charges times by the voltage drop across the crystal. So previously, everyone has always historically thought about this in terms of amplification. So what you can do is you can make a phonon amplifier. So it's like a charge to phonon amplifier. And in the limit that your voltage gets large, your total energy is just proportional to your Q. Your gain is just the voltage bias divided by the average E times delta V divided by the average energy per electron hole pair. So that's good. And this idea has been around again since 1990. Paul Luke at LBL thought of this idea. And, but the problem is exactly and I'll go back. The problem is exactly what we talked about earlier with LZ. So LZ has an E field This has an E field. And therefore, you would expect, just like LZ has leakage, this will have leakage. And here, this is exactly what Paul Luke saw, that as you increase the voltage bias, your signal stayed exactly, your signal was gained linearly, your noise stayed exactly the same, and then suddenly your noise started to increase rapidly. That's because you start to have charge leakage across your crystal. So your charge leakage across your crystal is random. It starts to give you random phonons. Those random phonons start to give you a lot of noise. And this is the core problem. And if you want to use a device with this kind of amplification scheme, you may have exactly the same problem that LZ has. You're going to have this low energy leakage events. And you won't be able to be sensitive to electron recoil dark matter. So this is a fundamental problem. We've actually seen this in super CDMS as well, sometimes at very low E fields. So if one doesn't have that problem, what can one do with this preferential, with Luke-Neganoff gain? And there's a few pretty cool things one can do. So the first thing we want to talk about is preferential stretching of electron recoils. And again, here we're trying to come to how can we get to that coherent neutrino floor between 6 GeV and 100 millieV, and 100 MeV. Because we need, in germanium, you need factor of 40 electron recoil, nuclear recoil discrimination. So let's see how Luke-Neganoff gain helps to give us that factor. So here in dots, in dotted, I have some distributions. And I'm saying, I don't know, I have a dark matter candidate which has a cross-section of 10 to the minus 43 centimeters square, and it's at 3 GeV. So here's our 3 GeV dark matter candidate, and this is the signal I would get in an event rate of events per keV per kilogram year, is this signal. And here is my background. So I have a bunch of cosmogenic lines, and I have my Compton background here. Now what happens when I put it, and that's at 0 volts in dotted. Now what happens when I put a voltage across the system? So I put a voltage across the system. Electron recoils, they make more electrons per recoil energy. So the yield is high, it's 1. So I'm going to make lots of electrons per keV for electron recoils. And that means the Luke-Neganoff gain is going to be big. So I'm going to put them out. I'm going to stretch my distribution to very high energies. And that means the average, the number of events per energy is going to drop from this down to here, this black. And actually, this cosmogenic line is that right there because I get gained. So my signal gets gained, but it also gets stretched. So as I stretch my signal gets flatter because the area is conserved. So my nuclear recoil signal doesn't get stretched as much. So this means that the signal I couldn't see before is now above my background now. So I have this preferential stretching. So what happens to this preferential stretching in the limit of having signal electron hole sensitivity? Well, that's what we're showing here. So now we have this signal electron hole sensitivity just like DOMIC. And you have 1 electron hole, 2 electron hole, 3 electron hole pairs. And if I have 100 volts across the crystal, it's 103 EV, 206 EV, 309 EV. And now my nuclear recoils, they, on average, take 30 EV per pair, let's say, to make a single ionization. So therefore, the average energy, if I have a 30 EV nuclear recoil hit my detector and it makes 1 electron hole pair, that's going to give me 130 EV total energy. So it's going to be offset. So my nuclear recoils, because they have lower ionization yield, are going to be in between my electron recoil peaks. I have quantization, I have discrimination, right? So I've automatically picked up discrimination because of this difference. So this is a neat thing you could potentially do with Luke-Neganoff gain that you couldn't do. This is new. This is where Luke-Neganoff gain isn't giving you amplification like we historically thought. It's giving you discrimination. So once you have excellent energy sensitivity, Luke-Neganoff gain gives you discrimination. It doesn't give you amplification. This is a pretty new idea.
How well does it work at the higher energy range?
It works very, very, very badly. Oh, yes. No, so how well does this trick work at the higher energy range? And the answer is, it doesn't. So as these things get spread out, so let's just think about what, Poissonian statistics or anything, it goes as square root of n. So as those two things start to go out, you'll start to lose this discrimination. So this only works at low energies, only works near threshold, but that's OK, because everything we're looking at is a near threshold signal anyway. But you're totally right. You're not going to get this if you're looking at 200 electron hole pairs. You won't say the nuclear recoil is at 200. So things are going to get problematic. So we talked about charge breakdown. It's real. It exists just for us, just like for LZ, just like for DOMIC. In fact, this is one detector which has really bad charge leakage, just to show you it really is a problem. And you can see that here is this is a very sensitive device. And you can see that even at something like 3.7 volts, we actually started to see extra noise. So if you have a bad contact, this can completely dominate your signal, and it's a problem. So what have we done recently to solve this problem? Well, we've gone to a very small device. We've gone to gram-sized devices, just so we can understand what this leakage current is, why does it exist, where is it coming from. And so we went to a 4 millimeter by 1 centimeter by 1 centimeter device. And we built a device that basically looks like a supercity mass detector. And here's the experimental setup. We just put some 1.9 eV photons with a laser going down and hitting the device. And here's what we see. So we were able to see, just like DOMIC, we were able to get to single electron hole sensitivity. So you see the 0. So this was for in EV. So this was for 160 volt data. So you see we have a 0 peak and a 163. 163 times 2, 326, I guess, EV going up. So that's great. Notice some problems here. Notice that in between our peaks, we have some stuff, right? We have to understand. We're certainly not going to be doing nuclear recoil, electron recoil discrimination with this device to the level we want, because the peaks aren't perfect. We're putting an electron recoil in. This should be super clean. We have some stuff in between we don't understand. So let's talk about that. Oh, yeah.
Are you using silicon or germanium, or you could use any crystal, or why are you choosing?
So the question was, why choose silicon and germanium over any other arbitrary crystal? And it's a great crystal, a great question. So the answer is, from the previous talk we gave, right? The lower the band gap, the better it is. And so we saw that for electron recoil dark matter, we saw that the rate scaled between xenon and germanium of 10 to the 3. So between those two band gaps, we got a huge advantage by going to a very small band gap. So you want to go to a small band gap. Semiconductors are semiconductors because they have small band gaps. So you're going to want to go to a semiconductor. Now, exactly which one you want to go to, that also depends on so silicon, germanium, or germanium has the smallest band gap. Silicon's the next. Gallium arsenide's the next. So gallium arsenide is somewhat problematic because even though I think, again, the semiconductor industry has spent an enormous amount of effort trying to make pure gallium arsenide, it hasn't achieved the level of germanium. So germanium has an impurity level. It's the cleanest crystal we've basically ever made. It's the cleanest non-metal crystal we've ever made. It can have a impurity density of 1 e to the 10 per centimeter cubed. And you say that's 10 to the 10 impurities per centimeter cubed. That's an enormous number. But in a centimeter, it's a huge number of atoms, right? So it's actually a very sensitive, a very pure crystal.
Why is the difference? Where do you get your germanium from? Is that just that?
So why is germanium? The question is, why is germanium cleaner than silicon? Yeah, so silicon is about 2 orders of magnitude. The cleanest silicon you can buy is about 2 orders of magnitude more impurities than germanium. And the answer is germanium has a low melting point. So germanium's melting point is a few hundred degrees lower than silicon. And so when you make these crystals, you're pulling these crystals out of some melt, and impurities will diffuse from everything. So like, I don't know, your crystal holder is quartz, or it's going to be some super high temperature metal. And the higher temperature you are, the more these impurities can diffuse, the more they can get into your melt, the more they crystallize out. So the moral is germanium is just, because it has low temperature, you can make it more pure than silicon. And so that's why germanium is such a pure material. And also, of course, it's just because we've worked really hard at it. Again, the semiconductor industry is the friend here. Like, they spend an enormous amount of energy trying to make clean silicon and clean germanium over decades. And so we're just being helped along by their efforts. We could never afford to do this on NSF grant money. So it's very nice that someone else has done it for us. OK, so that's why we're using silicon. So now let's look more and more at that stuff that is basically in between these peaks and that dark current. So here is actually here is our background spectrum. These are a bunch of randoms. And here, this is that leakage current signal. And the first thing you can see is leakage current signal scaled with lights on and off. So clearly, we have an optical photon leak. If we turn the lights off, our leakage current goes down. That's a good sign. That means that's not intrinsic to our device. It means we just have to make sure we have no light holes. So we've gone back and we've upgraded our system. And we've made ourselves much less light sensitive to the outside world. And via switching to a new fiber, putting IR filters on our system. And hopefully, we're going to drop this further. Here is actually this same signal, except we subtracted off this 0 background distribution just to see exactly what this looks like. And you see that spectrum here. So this is 1 electron hole peak. So one of the things you see immediately that's very interesting is it's not like every leakage current event is a single electron, has a single electron's energy. The leakage current events seem to have an energy which is sort of flat between 0 and 1 electron. So what is that? So we're going to call this bulk dark current. And so if I have a surface event, so let's think about LZ again, right? We talked about LZ. I have a high voltage across my system. I have leakage current into my xenon gas, which then goes across and gives me a single electron hole event. So here, we actually see exactly where it comes out. So if I have a current that leaks off my grid and goes across, that'll give me 100 EV of energy if I'm at 100 volts. So how do I get 50 volts, 50 EV of energy? Well, I need to have leakage that starts here and goes across only half my grid. So that's going to be, what are the two mechanisms for that we have thought of? Well, one is subgap IR, and that I have an impurity state here that's neutralized in my crystal. I have 10 to the 10 after all, so I have lots of them. And now a subgap IR photon, let's say 10 Kelvin, 1 millieV, comes in, interacts with my crystal, excites a single carrier, and then that goes across the rest of the way. So that's how I can get a, so the solution there, of course, is to just make my system more and more light tight. And I can hopefully get rid of this. The second possibility is I have that impurity that's sitting here, it's neutralized, and there's an E field across it, and I can tunnel it out. And maybe I have just autoionization. Those are the two ways I could get this bulk effect. But anyway, they're there. The remaining questions are just like as LZ. What is the size of this bulk effect? And is it Poissonian? And unfortunately, I'm not allowed to answer either of those questions because we're in the midst of writing a science paper as we speak on this device. So it turns out that a gram day, we just talked about that with electron recoil dark matter. A gram day of silicon is worth something like a ton or something like a kilogram of xenon. And so a gram day at the surface can give you world-leading results today if your leakage is under control. So both Dominic and us are trying to get to that gram day threshold so we can beat xenon 10. So that's actually this very interesting world we live in right now, is because one only needs a gram day of a semiconductor with single electron hole sensitivity and no Poissonian noise to have world-leading results. And so you should see a paper on this somewhat soon, in the next probably 2 months, of where we convert these spectrums to WIMP limits, or to dark matter limits in the 1 MeV to 100 to 100 MeV range. OK, so I want to go. So that was my stuff. I want to talk about other ways that one can get amplification. And so we talked about CCDs in the last talk. So in Sensei, we talked about how they get their sensitivity. It's not by amplification at all. It's just by taking that single electron hole pair and putting it on a very low capacitance sensor. We talked earlier in this talk about how one can get how one can fundamentally get great sensitivity, and that's going to low temperatures and doing all this fancy athermal phonon physics. Then here I just finished up a first possibility of how you can get amplification via Luke-Neganoff gain. And now I'm going to talk about 2 other amplification ideas. And the first is absorption amplification, and it's on helium. So helium I talked about in my last talk on purpose. And sorry, I skipped one. So here's superfluid helium. So superfluid helium, just like semiconductors, just like scintillators, which have long lifetime photon excitations, superfluid helium has many long-lived excitations. It has phonons and rotons that have very long lifetimes at the millieV scale. And of course, it has photons as well at the 18 eV scale. So the hope is we talked about that basic principle of the excitation detector, which was the PMT. And then we used it for athermal phonons. The question is, can we do the same thing with superfluid helium? Can we make a superfluid helium roton detector, which is just an excitation detector of superfluid helium? And there's one, and the idea is, so again, an event comes in, interacts, produces a bunch of phonons and rotons. The rotons bounce around. And every once in a while, that roton is going to hit this surface, and it will actually pop out. And a roton, a vibration that pops out, actually is a helium atom is going to fly across and hit some sensor up here. And so why is that important and why is that cool? Well, here is the energy levels for my system. So my roton is something like a millieV scale. And then for him to get out of the superfluid helium takes about 0.6 millieV, so he has to be above that. But if he has an energy above 0.6 millieV, he can eject a helium atom. The helium atom will fly across. And then if this surface here is bare, it actually will get pulled in, and the work function is could be huge. So the work function for that helium atom to be pulled in is not just 0.6 millieV. It could be 9 millieV, as it is in silicon. There's some materials where this is up to 40 millieV. And the idea is this is an amplification idea, right? So what you're measuring here is this energy here is going to all be given off as recoil phonons in these sensors up top. And you could get a gain of something like a factor of 10. And so notice that this gain is unique in that every other system where we are using gain and using these ideas of concentration of excitations, where in a PMT, how do we get our gain, our current gain? Single photon comes in, gives us, I don't know, 10 to the 4 electrons. We get it through a very big E field. In Luke-Neganoff gain, we have a big E field, right? So both of those systems have giant E fields to give us gain. This is a system that has no E field at all, and we're still getting a gain. So the hope is that because there's no E field, the hope is that the dark count rate will be very, very tiny. and that we'll be able to get amplification for free even without any dark count, without any tunneling effects. So that's the basic concept here of absorption amplification. So there is another idea that floats around there, which is phase transition amplification. And I think this has been floating around. Some Russians had some ideas of little mini bombs going off when dark matter hit it a while ago. But here we're going to talk about, I guess, a little more standard configuration, which is a magnetic bubble chamber. It was proposed by Sergit and Giorgio and a few others at Stanford and Berkeley. And the idea here is let's have basically a bunch of little tiny magnets, and let's prepare them in a state. So let's put a giant B field down, and the B field is first in this direction here. And the B field is so large that it forces all the spins to align with the B field. So we have all of the magnets pointing with spins upwards. And then we take away the B field and we put it in the opposite direction. And of course, this crystal must be pretty cold, right? It must be below the critical point. So once you set up the magnetic field, it'll stay magnetized. And now we're going to put the B field in the opposite direction. As long as the B field isn't too big, it won't be able to spin flip every single one of these. They'll be in a non-equilibrium situation. They'll be in non-equilibrium. They'll be stuck upwards, even though the external B field is pointing downwards. And from an energetic perspective, one would say, oh, thermodynamically, all of those things want to flip downwards. But it's impossible to have all of those flip at the same time. So they're just stuck up here in a very non-equilibrium situation. Now a dark matter event comes in, hits one of them, and it starts to heat them up. And once they're hot, now those spins can flip. And if you get enough of the spins here in the middle of this crystal to flip, then it'll start flipping all the other ones around it. And eventually, it'll go through this avalanche process where every spin will be flipped downwards to match that field. So in this process, a bunch of energy is being given off, right? And in some sense, you could put a little thermometer on this thing, and you could measure all that energy. But rather than measuring the energy, an equivalent way to think of it is you could just measure the change in the B field of the system with some kind of very sensitive squid loop. And again, if you think about the system, you say, where do you guys think there could be leakage current here? Or is this an amplification system that has leakage current? What do you think? So there's one possible candidate, I feel, and that is it's a little bit tricky, right? You want this thing to be just big enough that a dark matter candidate can put a little bit of energy and can cause the phase transition flip and can flip it down, but you can't have it. So you want a very little amount of nuclear recoil energy to cause this shift, but you don't want, for example, a Compton flies through, randomly hits the detector, gives a little bit of energy to an electron. That energy is going to fly through. That energy will also thermalize. So you need to have the system set up at this perfect place where electron recoils will not give you thermalization and will not flip you over, but nuclear recoils will. And this is actually how bubble chambers work. So if you heard of PICO, this is actually the concept behind PICO. And you ask, well, why doesn't PICO have electron recoil and nuclear recoil sensitivity at 3 keV? And it's the answer that to have their energy threshold be at the 3 keV scale, they have to basically put the system in such an out of equilibrium state that they start to have randomly, every now and then, an electron recoil hit their system and also flips it. So you start to have a problem that any electron recoil can start to flip your system as well. And you're sensitive in these kind of systems to not only electron recoils that are in your band. So we were talking earlier about this idea that the lower you go in energy, the less electron recoils are in your band. And that was just this idea of if this is my Compton background of electrons, and this is my signal for, I don't know, 100 GeV WIMP, then you're sensitive to all the electron recoils that are throughout this region in electron, if this is my ER. But if this is my electron recoil spectrum for a GeV WIMP, then I'm only sensitive to those in this range here, right? So I'm sensitive to fewer. So that's because I can measure energy of my pulse. Here I don't have a good energy metric. Because it's an avalanche, every event has exactly the same amount of energy if it's an MeV or if it is 10 millieV. And therefore, you don't have this benefit of being able to say, oh, that's a 2 MeV photon hitting your detector. You're going to get drilled by this. So I think the math says that they can survive and they can actually do these very tiny nuclear recoils. But I think that is that's certainly the biggest potential of dark current, and because you're sensitive to the entire spectrum, and so it's an open-ended question of this will work. But I think any kind of phase transition has this. You put a system in a non-equilibrium, and you can get enormous amplification, and it's a neat idea. So there's a few others that are of similar feel to this in terms of great amplification systems. People have done superconductors like this as well, where they're doing a phase transition in a superconductor from superconducting to normal. And that one definitely has a lot of leakage current associated with it, which is just random. But this is the final idea of how to get amplification without leakage current to do electron recoil dark matter. OK, so I skipped.
Question.
Yeah.
In Pico, for example, they can tune the threshold. It's a threshold experiment. They can tune the threshold, so they have some idea because they of course they measure any energy larger than. But you can,
Sure.
you can put your threshold,
Yeah.
which gives you some discrimination here too.
No, so here it certainly is true. I want to go back to that point. Oh, and I have to give you the question. So the question was, let's talk, because this is basically a mini Pico. All these sectors work the same. The question is can you somehow figure out what was the energy scale of your events and background subtract? So the key is that, and the answer is actually right here in this. And you can see exactly how one would do that here. So depending on how big that B field is in the other direction, so I set my system up. So I set my system up all spin upwards, and then I put an external B field down. If that external B field is really, really big, then it is very close to transitioning. And the bigger that B field is downwards, the more it really wants to transition. So if I just give it a little bit, if I give it 1 or 2 or 5 spins up, it'll flip. And yep.
So microscopically, what is it that's driving this collective spin flip wave that moves across?
Oh, no.
It seems to me that, I don't know how long that takes. It might not go to completion.
So it'll, absolutely. So if the field is not big enough in the downward direction, it won't go to completion. So let's say, if it goes to completion or not depends on exactly what the size of that B field is in the down direction, right? So let's say, for example, the B field is really, really tiny. Let's say there's no B field at all. The dark matter comes in, it thermalizes these spins. So now they go in a random direction. And let's say 2 or 3 start to spin flip down. That's not going to cause the others to spin flip. The others are going to say, I have hundreds over here, I have hundreds over here. I'm going to force them back into alignment with myself. So if I have no B field going downwards, it'll stay. As I start to make that B field in the down direction bigger and bigger and bigger, then I need fewer and fewer of these to be pointing downwards before it'll spin flip. So the bigger the B field downwards, the more likely it is to run away and go to completion and avalanche. And it is this very avalanche process. It's going well because when one flips, it releases energy, which helps thermalize the others, which help them flip as well. So there is this very nice process that it avalanches. But that's the problem. The problem is not can you get this? The problem is can you stop it from occurring when you don't want it to occur? when you have that electron recoil come through, when you have the muon go through, like, will it also occur, and will it be a problem? And so I think that's where the leakage current question is for this idea. But now going back to the question over here is you can tune that B field so that different size of recoils will either cause you to flip or not. And that's exactly what Pico and the standard bubble chambers do. They tune their effective recoil, which is just the pressure they have on the system. And they tune it. And so with that idea, they could do some background subtraction, right? They say, I only allow every recoil that's below 100 keV will give me a will give me a spin flip, and then that'll tell me how many, and I can go through and I can sort of map out what is the rate, and then I can background subtract that rate away from my signal. But that idea is fundamentally background subtraction. So it has square root n statistics. And so that means that if I'm not going to scale very, very quickly in time, it's a background subtraction. So I'm sensitive to the systematics on it, and I'm also sensitive just to the amount of time. At best, my limit will improve as square root t. So we would like to have systems that don't have background fundamentally, and that's a challenge in these devices. But maybe this device will be perfectly balanced such that electron recoils and muons and those things won't actually cause the thing to flip. And what that is that's the big question on this device. Because if not, it could actually be amplification with no problems. And definitely, I've shown that E fields and mechanisms with E field amplification, they have all seen problems at some level. I've also shown you that optimistically, both Sensei and us believe that those are manageable levels, that we can use Poissonian statistics to get rid of them and still look at the 2-electron hole bin and still have great results. But maybe this is the path to go down. In summary, so in this 10 millieV to 10 GeV region, at the core, what does one need? One needs energy sensitivity in some shape or form. If you get that energy sensitivity via amplification, you're good to go. If you get it intrinsically, you're also good to go. But somehow between that combination, you need to do it. So your detector backgrounds must be small, i.e. these dark count rates must be non-Poissonian, and must be manageable. Your radiogenic backgrounds, these are relaxed compared to high mass WIMP searches. This really drives, in many ways, LZ, right? Like you have to self-shield, like without, and if you talk about like the people, what are they worried about with the next generation of xenon experiments? They're worrying about intrinsic backgrounds, about dust in their xenon causing problems and making them so they can't self-shield. So this isn't as big of an issue because it's just not in our band. If your band is at 1 eV, you just don't have to worry about it. So I've also shown this concept of athermal photon sensor technology, which, intrinsically, if you're not doing any amplification, it's dark count free. So that's nice. Has intrinsic dark count capability. And I've shown you about TC cube scaling, and I've shown you the first steps we've taken down that path, where we're at the 50 millieV scale. So it seems promising. And Luke-Neganoff amplification is one technique that we use in our group. We've seen single electron pairs. Phase transition amplification is again a possibility that seems to have lots of promise. And then, of course, Sensei has been around now for a few years now with single electron hole sensitivity with their CCDs that show amazing promise as well in lots of this region. OK, thanks.
More questions?
Yeah.
For the phase transition applications, when the spin flip,
Yeah.
what's the detectable still?
Oh, yeah. So there.
Please repeat the question.
Oh, yeah, sure. So the question was on the phase transition amplification device. what is the signal? So here, actually, the signal is the B field of the spin flip. So what they have is they've put a pickup coil, which just measures the flux of the pickup coil. And when this thing flips, the flux of the pickup coil is changed. So now you're sensitive to that change in flux. And squids are, one of the truly amazing devices that we have made over the last, I guess, 30 years. Yeah, 30 years is about right. And they're the most sensitive current and flux detectors we've ever made. And they are just fantastic. This is what a large percentage of quantum computing is based on, is on qubits, which are basically squids. That's one of the many ways to quantum computing. And here, you can make them sensitive enough to be sensitive to a single spin flip.
And a strong B field just means stronger than the initial B field that set up the spins?
Yeah.
Okay.
So I have a question on the superfluid helium. In that study, you mentioned when the proton hits the surface, there's a probability that the helium atom gets ejected out.
Yeah.
Is that process sensitive to just the liquid vapor equilibrium of liquid helium?
Here, there is no vapor phase of liquid helium because you're very far, 4 Kelvin at atmospheric pressure. And you're going to be doing this at 10 milliK. So there basically is no vapor at all. But with that said, you actually hit on a really excellent point. So the group that originally did these studies was Brown for heron, which was a beautiful experiment back in the 90s. They measured some of these processes, and they found that process wasn't super efficient on that surface for kicking out. And they also found that the roton reflectivity on other surfaces wasn't as high as we would naively think. And that's surprising because superfluid helium it's a superfluid. It's so bandwidth mismatched to every other system. The sound speed in helium is it's at least 1/10 the sound speed of any other crystal. So you would think it would reflect just like in a dielectric. You have a wave hitting, it reflects very well. It's super surprising that you weren't getting much higher reflectivities on that surface. And I think Dan McKinsey, who is really the lead, so Dan McKinsey and Scott Hertel, who are really pushing this liquid helium idea now, I think part of their concept is they just don't think that Heron was actually trying to bump that reflectivity up. And that was because they weren't trying to make super sensitive devices. They were instead trying to be sensitive to KeV scale events. And at KeV scale, you didn't need to have great reflectivities. You could just say, I have mediocre reflectivity. And here, so the question is just, did they actually put the time and effort into really solving that problem? And maybe now that is the most important problem to solve to make liquid helium a viable experiment, we can do it. And so I think that would be the R&D necessary for liquid helium detectors, would be to actually see what are the materials, what kind of surface properties do we need to have to make that reflectivity really high.
Okay.
I have just one brief question. I hope it's brief. Is it well known how much of the energy of the matter particle will be transferred into photons?
Yeah, no, I can, oh gosh, do I have?
Efficiency of proton production.
Yeah, no.
For interparticle.
So I can give you the qualitative answer. And the qualitative answer I'm going to give you is actually one from friction. And therefore I'm 100% sure it's right. And I think it'll set the scale of what percentage go into rotons. And that's because in our crystals at Sudan, in Super CDMS, one of our backgrounds was actually frictional rubbing. And so frictional rubbing, of course, makes heat. and heats things up, as we know. The pertinent question, which is very similar to what you just asked there, is what is the phonon spectrum of frictional rubbing? And I think that is basically tantamount to the question you asked, which is what is because these are just phonons and helium, what is the phonon spectrum? And rotons are just think of a roton as a high energy phonon. It's just because the omega K relation looks really weird in helium. So the question is how many high frequency phonons are made in helium when something hits? And we see in our crystal that lots of high energy phonons are made when you have frictional rubbing. So if you have two surfaces rubbing together at 10 millik, it makes athermal phonons. So why are athermal phonons produced when you have two surfaces up against each other? And let's just think about the macroscopics. So the microscopics. The microscopics are, I have just a bunch of atoms on springs, and when I rub, I get one atom stuck in a high potential system, and then he can tunnel across and release all of his potential energy, right? And the length scale of that thing that happens is the length scale of the atomic spacing. He goes from one place to another. He moves by an atomic spacing. And so that's the vibration you produce. So if you look at that in frequency space, that is basically phonon vibrations all the way from 0 to the Debye frequency. So if you have a single atom move an angstrom, that's actually the superposition of phonons that are all the way from 0 to the Debye frequency. So you make athermal phonons. So anytime you hit a single helium atom, you always make athermal things, because you're actually exciting the entire phonon space. And so one would expect, by that analogy, that that's exactly what you're doing, right? Like just that alone tells you that when this thing comes in, at first it's going to make athermal phonons, and then those athermal phonons are going to downconvert. And what will happen is, in this case, they'll get stuck as rotons. So that initial process should be a large fraction of the initial process should be rotons.
So will there be a discrimination between electron recoil and nuclear recoil?
Between electron recoil and nuclear recoil with that? Absolutely, there should be. I think so Dan and Scott have two different techniques. One is to do the standard scintillation versus phonons. So in that sense, it looks very similar to super CDMS, where you have these two channels and you look at the yield ratio. And that should certainly be there. The slightly more subtle question is, what about looking at photons and looking at this time spectrum of how the photons drop out? And that's because, and I don't have, yeah, I could draw, but there's a chance that you could have more distinct or more subtle features that one could do electron recoil and nuclear recoil discrimination on. I'll say that. So there's some proposals, and we can talk about it afterwards if you guys want.
Okay, so thank you, Matt.
Oh.